I'm going to talk about some of the work that we did in Scandinavia for the last maybe 10 years on research that we did for the fire service. And my background is, very quickly, I did my engineering degree in Edinburgh. I then did my PhD in fire safety and risk engineering at Lund University. And I was an associate professor there for a long time. And one of my students was a guy called Stefan Svensson. And I had several other students. And we were very interested in research for the fire service. And these guys, they were also part-time firefighters. So not very many people were doing research for the fire service. It was much more fire research for engineering design and stuff like that. So we got very interested in this around 1990 and so on. And so we started doing little bits of research. And I'm going to talk about that today. So I'm currently, like everyone in Iceland, everybody has 2 jobs at least. So one of my jobs is I'm the Director General of the Iceland Construction Authority. That's my main job. So we are in charge of fire safety regulations, electrical safety regulations, and building regulations. And we also run the Fire Service Academy in Iceland. So we teach firefighters and fire officers. I'm also an associate professor at the university. But one of the things I did about 15 years ago, I published a book called Enclosure Fire Dynamics. It's more for engineers and engineering and design and things like this. Together with a good friend and a well-known researcher in America, Jim Quincheri, professor at the University of Maryland. And so my students and we tried to take the knowledge of physics and chemistry and express it for people who didn't have many years of mathematics and physics, for firefighters. And we published sort of books for educating firefighters. And I'm going to talk about these books. One other thing that I should mention is I sit on the editorial board of Fire Technology, which is the latest issue. This is research in fire safety science. In the latest issue, absolutely brand new, there is an excellent paper by Stephen Kerber at Underwriters Laboratories. And so it's great to see UL represented here so well. They are one of the very few organizations who do some serious fire research for the fire brigades and firefighter safety and stuff like that. So it's great to see those guys here. My lecture today, I'll sort of give a quick background. I will then talk about these 3 phenomena: flashover, backdraft, smoke gas explosion. In the firefighting community, people have used all kinds of words for these. Some people talk about lean backdraft, rich backdraft, rollover, flameover, all kinds of things. When we started looking at these things, then there is not a good correlation between classical physics and chemistry and some of the names that we have been using, some of the terminology we've been using in the fire service. So, lean flashover, rich flashover, it's not correct according to physics to talk about those things. And that's one of the reasons why we went into some of this research. I will then talk very briefly about some work we did on fire ventilation, fire suppression, on tactics, and give some conclusions. All this is also described in a 12-page paper that is available. Ricardo has a copy of this. So if you want to read more about the background, the paper is, there's a paper available. So one of the reasons we went into doing this research is that the buildings in our environment are getting more and more complicated. There are all kinds of tall buildings, atria, glass facades. There are complicated structures underground, sometimes underground shopping malls, where people have to escape up through escalators the same way that the firefighters have to come down and stuff like that. So our environment gets more and more and more complex. At the same time, our understanding of all kinds of fire phenomena has increased very much. And at this time, we have simulation programs and things like that, calculation procedures that where you can simulate fire, the fire behavior. So we have a lot more knowledge now than we had maybe 20 years ago. And it's very important to use this new technology and this new knowledge in the fire service and in training. And I will give a sort of an overview of some of the work that we've done at Lund University on this area. With regard to flashover, backdraft, and smoke gas explosion, these are very hazardous phenomena, and there has been some controversy over all kinds of terms that are used. We did a research project with the aims of clarifying the terminology, increase an understanding of these phenomena, the dominant sort of physics and the dominant chemistry. And we wanted to produce a basis for teaching materials so we could actually push this out to the fire service. And this is a kind of a typical view of the stuff that we concentrated on. This is temperature and time. This is kind of a typical fire development. Something develops, and you can either go all the way to flashover if you have a well-ventilated fire. If there's an opening, so you have a lot of oxygen coming in, then the fire can grow all the way to flashover. It can burn for a long time and then cool down. But very often there is a lack of oxygen at some point, and the room is closed. You continue producing gases, and you will have unburnt gases. The temperature will drop. Then something happens. Somebody opens a door, or a window breaks, or something like that. And a number of things can happen. It can actually just go out. Or you can have what we call a backdraft, where an extremely rapid thing. It's seldom observed, but quite a number of firefighters have died because of a sudden backdraft. Or the oxygen comes in, the air comes in, and it just grows to a flashover and becomes a... So these are the kinds of things that we looked at, did a lot of experiments on this, and we want to inform our firefighters about the chemical and physical processes that are involved, and we want to show them some of the warning signs when something is actually just about to happen, and how to deal with these problems. So a compartment fire can develop in very many different ways. Not all of these are hazardous. I'll give some examples here. When we have a fire development in a well-ventilated space, so there's a big opening, a lot of oxygen. This is a very common situation. If it's just contained within the one item, this is easy to deal with. The fire hasn't spread, and it's relatively easy to deal with. But when the well-ventilated fire leads to flashover, this can be very difficult. In Sweden, anyway, we figure out it's about 5 or 10% of all building fires. And the warning signs here are very important. What we're talking about is like this. This is a typical experiment. There's temperature and time. Something starts burning. It cooks. And then it sort of, the whole room cooks. Just wait, 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 wait. And then suddenly we have flashover. So it's a sudden event. And this is where we extinguish. There are many different colors here. The highest temperature is near the ceiling, and then we measure the temperature coming down, and so and so. But it's always a it's a sudden event. It's something that happens suddenly. You all know this, of course, but we have to show it and measure it. So we did a lot of there's a lot of experiments that have been done, and Pravin just showed some of them. Some of the warning signs: there's an increasing speed of gas suddenly coming out, the neutral layer suddenly, or the layer suddenly goes dump, and you get the flames coming out. Some people say that there's a good warning sign is the color of the smoke. If it's very dark, there's unburnt fuel and stuff like that. But this is not a very good sign, actually, because of all the modern materials that we're using today. The smoke can be gray. Some people say that if the smoke is gray, it's not that much. It's not difficult. It's not very hazardous, likely. But that's not the case, actually. You can sometimes have, depends on what's burning. There was a fire in the dockyards in London. It was a smouldering fire. It was mattresses, lots of mattresses burning. They produce a lot of gray gas. When the fire service arrived at the scene, they took a hole in the roof, and suddenly there was an enormous backdraft, and 2 firefighters died. They thought they were looking at the gray gases and thought it's not that difficult. Not a lot of unburnt gases, they thought, but so the color of the smoke is not a very secure thing. I'll just show. Now let's have a look at fire development in a very poorly ventilated space. There's a lack of oxygen and the temperature decreases. What can happen here? There are 4 quite sort of common outcomes. It just dies out. It just dies out and self-extinct. Sometimes you have auto-ignition of the gases. I'm going to talk about what that is. And sometimes you have flashover, sometimes you have backdraft. I'm going to go through these very quickly. The self-extinction is very common. There's a fire in a closed room, burns, and then it just dies. It's quite a common thing. It's easy to deal with. It can still create dangerous conditions for people still inside the building. The smoke can somehow go somewhere through the ventilation system and harm people elsewhere in the building. But for firefighters coming in, it's not a very dangerous thing. This is what we call auto-ignition of the gases. This is when the gases are up around maybe 600 degrees. When we say auto-ignition, we mean that there's a lot of unburnt gases, and you don't need a spark or ignition to ignite them. They are so warm, they're about 600 degrees or something like that the molecules are moving extremely rapidly and they just suddenly combust. So it's called auto-ignition. And then usually something happens, like a window breaks or something like that. And we get some kind of an outcome, either backdraft or growth to flashover or something like that. If the gases, this is not very common, it's only if the gases are extremely hot. More common thing is that the temperature goes down. We still have a lot of pyrolysis from the burning surfaces, a lot of unburnt gases, and then something happens when somebody opens or something like that. So that's where you have to be very, very careful. And I'm going to talk about these two phenomena. I'm going to talk a little bit about backdraft. I'm going to show you a bit, some things, some films of this. This is what we feel one of the most hazardous situations that can occur when a firefighter is fighting a fire. And many firefighters actually have died because of these things. Conditions favorable for a backdraft are where you have a well-insulated room. So there isn't very much oxygen coming in. And very often the fuel is placed in the upper part of the room, so it continues to pyrolyze. It's very hot up there, so it continues to pyrolyze, and a lot of unburnt gases are produced. Often it's a smoldering fire that's been ongoing for a long time. And you have a lot of unburnt gases. They have mixed with the air, and so on and so on. Sometimes it doesn't mix, sometimes it's mixed. But then something happens, somebody opens the door, and an ignition source is there, and you will get the backdraft. How often does this occur? Well, we think it happens quite more often than people report, because it's sometimes difficult to define exactly what it is. Are there warning signs of a potential backdraft? Many people say the color of the smoke, if it's gray, it's probably cold, and it's probably not anything gonna happen. But I would not recommend using the color of the smoke as an indicator. Some people say, well, if it's black, it's a sign of non-complete burning, and so and so. So you have a lot of unburnt fuel. But this can also happen in if you're burning mattresses or some polyurethane foam or something like that. Some materials also have sulfur in it, so the smoke becomes yellow, and so and so. But it's not a very good warning sign for this. We took, and some people developed a new method for mitigating backdraft, a tool called the cutting extinguisher, which I could have possibly shown a bit. So this cutting extinguisher can actually cut through a solid concrete wall in just less than a minute. You can just cut through it. But it's dangerous if somebody is on the other side of the wall. So you have to be very careful using it. But it's actually a very handy tool. Now, warning signs are basically the fire may be pulsating. You have no visible flames. Actually, you don't see the flames. There are whistling sounds around the windows and the doors. And if it's been going on for a long time, a lot of unburnt gases may have accumulated, and you have hot doors and windows and so on. So be very careful in these situations. Now, I'm going to talk about the third phenomena that we talk about. We call smoke gas explosion. So we talk about flashover, and we don't divide that into different types of flashovers. We just say flashover. So backdraft. And the third phenomena, it's very seldom, is a smoke gas explosion. You may ask, this is the International Standards Organization definition of the ISO definition of smoke gas explosion. I'm not going to read it. I'm just going to tell you it. This happens in Scandinavia very often in conjunction with saunas. So you have a sauna in a hotel. The sauna is very tight, because you don't want air to come in. You want to keep it hot and nice. There's a lot of combustible material. It's usually made of wood. So combustible material, and you have some kind of a smoldering combustion starting there. We had 3 of these last year in Sweden. Always a sauna and a hotel. So what happens is you have a lot of combustion going on, incomplete combustion. The smoke then finds a way into a concealed space like this hidden ceiling, goes beyond here, And in this space, behind these tiles, there's a big space. The unburnt gases go in there, they mix very well with the air, and suddenly you have a perfect mixture of gases. You have maybe something like 5 or 6% of unburnt gas and 90% air. And all you need now is a little spark. Nothing happens, the firefighters come in, they shut down the fire in the sauna, and then one of the tiles falls down, and a little spark goes in, and boom, you get an explosion. So some people ask me, what's the difference between backdraft and smoke gas explosion? The very simple definition is this. A smoke gas explosion is a boom. A backdraft is a whoosh, okay? So that's the simple definition. Flashover would be a very long whoosh. It would be a whoosh. So those are the simple explanations of this. But a smoke gas explosion is actually a boom, and firefighters, they have died often far away, maybe 20 meters down the corridor, because there's a big pressure buildup, and a pressure wave comes and just hits them, and they die not from thermal exposure, but they die because of the pressure wave. So the sort of warning signs of a potential smoke gas explosion is this thing. Is there a sauna? Is there a sauna in the house? Is there a hidden ceiling? So, basically. And there is, of course, a gray zone here. Sometimes you get something, whoosh, was that a flashover or was it backdraft? And you get a very rapid flashover, sometimes whoosh, that's nearly a boom and stuff like that. So there's a gray zone in here that a lot of things can happen. So the results that we found was that some of these things, they occur relatively seldom. Flashover often occurs, but what we did to try to train our firefighters was that we wrote a book. These phenomena are closely related, and sometimes it's difficult to distinguish them. What we did is we wrote a new textbook for firefighters and fire officers, and we used this in the Swedish fire and rescue training facilities, also in Norway and in Iceland and so on. So in Scandinavia, we use this book, and I will leave it out here so you can have a look at it. This is Lars-Göran Bengtsson, who was one of my PhD students. So I'll leave this here for you to look at. Now I'm going to talk a bit more about backdraft, because we got very interested in this phenomena in the fire service also. So most of the fire research work over the last 40 years has concentrated on well-ventilated fires. So everything is open and so and so. So there's a lot of oxygen that comes in, so the fire can grow, so we can have a lot of temperature and a dangerous fire in this way. So most of the work on fire safety with regard to design and so and so is well-ventilated fires. However, if you have an underventilated fire, and this is very often the situation when the fire service arrives at the scene, you have an underventilated fire somewhere. We haven't researched this very well at all. Why? Well, partly it's because it's much more complicated. The problem with underventilated fires, you have to not only deal with classical physics and heat transfer and thermal things. That's the only thing you really have to deal with in the well-ventilated fire, thermal stuff, well, sort of classical physics. But when you have a closed room, suddenly chemistry comes into it, and you have to deal with very complicated chemical processes also. There's not enough oxygen, you produce a lot of unburnt fuel, and so and so and so, toxicity and this and that. So not very many people have done this. UL has done quite a bit of work on this and with regards to fire service, but not many people had done that. So our aim was to work some more on this backdraft phenomena, and we wanted to have a closer look at this, and so we built a special backdraft container. The graphics is better on my computer, but so it's a container where we have an opening in the front, we have an underventilated fire inside, and then a lot of unburnt gases are produced. Then we wait a bit, and then we open the container on this side here, and a gravity wave, it's called a gravity wave, cold air comes flowing in, goes and hits the back of the wall and mixes. And it's the 20 seconds, nothing happens for 20 seconds. The cold air goes in, nothing happens. It's when it hits the back wall and goes and mixes everything, that's when you get this really powerful, good mixture of gas within the flammability limits and a little ignition, and you will get a whoosh out. And so we use we built this in Revinge, which is one of the training academies. And so we do a lot of work. We show firefighters backdrafts. We show them what they look like. And here's a typical backdraft that goes out like this. I can show. And so this is a saltwater modeling. This is just to show what the phenomena is like. You see the green area? The blue area is cold, fresh air. No unburnt gases. The green, the red area is unburnt gases, too much. There's no way we can ignite it because there's no oxygen there. But the green area is where the unburnt gases have mixed with the oxygen. And so we can actually ignite this green stuff. And you see when the wave, the gravity wave, goes and hits the back wall, that's when the green stuff is big. Oh, yeah. So around there, you ignite it around there, you will get a very powerful backdraft coming out. So, and so we've simulated this, and slowly and gradually, if you don't have any ignition source, you're very lucky, and it won't ignite until later. But usually, we're not that lucky. So, so we've simulated this. We do a lot of, it's called CFD. It's computational fluid dynamics. So we have models that simulate fires in buildings. Okay, some of these models are quite sophisticated, and some of them actually have. Some of the weaknesses are combustion models, but now there's a trend to increase the availability of combustion models. So we can actually model this. So we model this in a. So this is a modeled combustion in the container, and we see that it's represented quite reasonably well. I'm just showing this to show you that the technology is like this. So I wanted to show you some of the. We did a lot of some work on the risk of backdraft versus tactics. So we had a room where we had an underventilated fire, and we wanted to test what happens if we have positive pressure ventilation and we try to push the gases out. And so we studied 4 different situations. We had an offensive attack, just a BA team entering from the front door. We simulated a defensive attack where we just opened some doors, one at the back, one at the front. And then we additionally put a positive pressure ventilation at a fairly high flow rate by the door. And then we did the wrong thing, which is put a positive pressure ventilator at the door, but we forgot to open at the back. So that's a bad thing. I'll just go very quickly through this. We tried to do this. I don't know if yes. So you can see where the green stuff is. That's where you can get backdraft, and so we simulated a lot of these, and a lot of these scenarios. And I'm not going to go through this now. There's no time. So we sort of worked on this, the offensive attack, and we showed the simulations. We did the defensive attack, the natural ventilation, and we figured out where's the green stuff. And so we measured what the.
You can take some more time for this.
Yeah.
Yes.
Okay. Okay. So this is like, for example, 10 seconds into the into what's happening, and it shows you that this is where you get least of the green stuff, if you say so. But it all depends on the geometry and where you open and so on. So this is just a single scenario that we studied. The incorrect use, that was this is 35 seconds, but after 10 seconds, it's actually a lot of green stuff there. We mixed up all the oxygen and the unburnt gases. There was a lot of green stuff there. So this is the kind of stuff that we work that we did on backdraft specifically, and we sort of discuss it in these books. Another area where we did quite a lot of research, and especially Stefan Svensson. I'm going to show just 3 of the projects we did. We did an experimental study of fire ventilation action during firefighting operations, and we did an experimental study in a large hall, and then we did a special positive pressure ventilation project also. And I'll just quickly go through this. This is we did experiments in a firefighting training facility at the Revinge Fire Academy. I'll show you a photo of it. This is just a small fire. It's a half a meter diameter heptane. So it's only about 400 kilowatts or something like that. But still, it's going to be a bit more than a meter flame or something like that, a meter and a half. And then we used positive pressure ventilation by a fan also. And we did 15 experiments in this series. This is the house, so this is the stairway, and this is the second floor apartment that we have the fire in. And we want to check what happens when we use different tactics. So this is the way we come up the stairway. This is where we put the fan. This is the door into the apartment. And this is the window that we open on the other side. And we had a lot of measurements here. Basically, thermocouples to measure temperature and things like that. And pressure probes to try to figure out what the velocity of gas out through the window would be, and so and so. And so we did a lot of different scenarios. We had the window closed, we opened the door. We had an attack through there, and through the window, through the staircase with the window open, through the staircase with the window open, and a positive pressure ventilation fan, and so and so. So we did did all these. I'll show you some of the results later. So this is one of the experimental series we did. Another one, we decided we want to do a large hall. So we did 5 tests in a large hall, which is about 40 meters long and 11 meters wide, 8 meters high. So it's a large hall. We wanted to try some stuff there. And we had a much bigger, quite a bit bigger fire, about 1 megawatt. So that's a couple of meters high flame. And we tried some ventilation tactics. We tried opening up here and opening up here, and just ventilation through natural. And we had a positive pressure fan here, and so and so. And we investigated just through the door, window at the ceiling level near the northwest corner, and so and so. And then we had a fan located 3 meters outside the main opening and blowing into the hall, and so and so. So we did quite a few scenarios, and I'll show you. And thirdly, the third test we did was 43 experiments on the first, second, and third floors of a 3-story brick building with wooden trusses. This was only cold flow, so we didn't have a fire. We just had smoke. We just made theater smoke. It's too big. So we did this, and we did a lot of different tests in this building, but with cold smoke. Okay, and we did all kinds of tests and measured them. Now, the results basically can't really talk about them very much, other than just showing the book. Basically, we find that positive pressure ventilation increases the mass loss rate of the fuel if you when you push the oxygen in, and so and so. This is everything. This is stuff you know. This is no news to you guys. But what we actually did was we produced a teaching book for firefighters and fire officers, especially fire officers, on fire ventilation. Stefan Svensson is the author of this book, and we go through here how to ventilate and so on. So I'm not going to go through it. We're going to have master classes this afternoon, and UL will show you some of the great research they have done on this. I will also talk a bit about some horizontal ventilation. So we'll go into the details there. But I will leave this book here. You can look at it during the break. So it's this book here by Stefan Svensson. We use this to teach our fire officers in the academy. Just a few things about suppression. So we did a couple of series of experiments. We did live fire tests on suppression of post-flashover fires. So we tried manually applied sort of high pressure hoses versus low pressure water sprays. And there's a big discussion in the fire community. Which is better, high pressure or low pressure? And it's nearly a bit like religion sometimes. We don't use high pressure. We only use high pressure, and so on. So we wanted to check this out. The truth, of course, is that sometimes high pressure is good, and sometimes low pressure is good. So I'll show you some. They found out that high pressure was good, actually, but that's only for that experiment. See, so. And so we can discuss this a bit later. And then we did fire tests in a large hall, again, high and low pressure water sprays. And the first series, we had a 40 bar high pressure system and a normal sort of 10-bar high-pressure system. And we had 15 tests in a firefighting training facility. And so we applied the water in a controlled fashion, and we used actual firefighting techniques. And the fuel was applied on the walls and the ceiling of this fire compartment. So this is the kind of thing. The firefighter goes in a certain way and then sprays on the fire. The second test was in a large hall, and so we wanted to compare high pressure with low pressure and so and so. And we also measured the heat stress on breathing apparatus equipped firefighters. We did 6 tests in a room that's fairly large, 14 by 8 and 6 meters high. And we had a lot of, we had quite a big fire actually. It's 13 pallets in each stack. So it's maybe about nearly 5 megawatts and maybe 3 or 4 meters high flames. So it's quite a big fire. And so this is the layout, and the firefighter entered through this door and stopped at a certain place and tried to put out the fire. And we measured some temperatures and things in there also. And so this is what they found out in these 2 scenarios. They say that the high pressure system decreased the attack time and reduced temperatures quicker. But that's only in this scenario. In other scenarios, it is better to use low pressure. We can discuss this later. Why? Well, the reason is fairly simple. The high pressure will produce very, very small droplets. And the small droplets, they travel very well, and they do an excellent job at quenching the flame. So in the gas phase, the small droplets have a lot more surface area, so they can cool the gas much better. So small droplets, high pressure, they do a very good job of quenching the flame itself. But they go with the flow. So they can't go and reach down into the surface of the actual fuel, of the wood that's burning. So the small droplets do a really bad job of cooling the surface. 2 ways to do this. Either you cool the flame so that the combustion has to stop, or you cool the surface down to maybe 300 or something, and it can't produce any more combustible gas. It can't pyrolyze anymore. The heavy droplets, they go through the flame and through the flow, and they go straight down to the fuel, and they stop the fuel from producing gas. That's very good for that, but it's very bad for cooling the flames and extinguishing the flame. The fine droplets, they do the flames, they're very bad at cooling the other. So sometimes if you have a fire under a staircase and the heavy droplets, they just can't get there, the fine droplets will find their way there through the flow. They will quench the flame often. And so and so. So there are good things about high pressure. There are bad things about high pressure, and so and so.
Let me ask, in this experiment,
yes?
what the rate of heat release are you talking about?
It's something like 4 or 5 megawatts. Okay. It was a pallet stack, wood pallets.
And they could extinguish that with only one high pressure hose?
Yes, okay. They could. They say, but they are. They like high pressure, you see. So we will see. So when both the surface cooling effects and gas phase effects are considered, the high pressure required less water. the increase in firefighter pulse rate appeared to be triggered by stress and increased due to increasing skin temperature. So we monitored the skin temperature and the pulse. And so we've got some experiments there that we're doing some work with the medical faculty, the doctors, to figure out some things about this. And so we produced a book on water and other extinguishing agents. So we tried to boil this down to language that human beings can understand, not just equations and stuff. So they don't say that high pressure is better, it's just different. So this is Stefan Särqvist, who is also an old friend and a student of mine. So we did some work on tactics also, what tactics to use. And so I'll just see what time it is. So, okay. So very quickly, we wanted to study tactics, tactical patterns, and investigate firefighting tactics in a special mechanical workshop and in a residential type of structure, and implications for firefighting operations. So what do we do? Do we ventilate? Do we go suppression? Do we send in breathing apparatus people? Or what do we do? And we did quite a few. We did 20 experiments in a firefighter training facility. 8 standard wooden pallets used in each. So it's not a very big fire, but it's a couple of megawatts. And we wanted to ask questions: why do we ventilate? Why do we suppress? Why do we? What if we do this first and then the suppression? What if we do the suppression first and then the ventilation? And what will come out of it? And so the basic idea is actually a systematic systems study. There are a number of choices. What happens if we do this first, then the other, then the third? What if we reverse the order, and so and so? So this is the test facility we used. And so we had people coming in, extinguishing the fire here. We could open here, we could open here, we could have a positive pressure ventilation here, and so and so. And we measured the temperature. So we measured, we said the measurement of success is temperature and time. So if we lower the temperature quite a lot in a short time, then that's success. Okay? You can argue with me about this. But this is the simplest way of doing it. So we did all these. I'm not going to go through this. We did about 20 different kind of scenarios, doing this first, this second, using this then, and so on, so on, so on, so. We mixed these up, and we measured the temperatures for each, and we compared the strategies. What was the best strategy? Well, how we quenched the fire. And you can find that when we put these up, this is, for example, 19. That's a certain strategy. Do this first, then that, then open, then positive pressure ventilation, and so and so. So when you set up these scenarios, you find out that in some cases the temperatures were actually quite low, and that's a success. Whereas in other cases, it took a long time, and the temperature was quite high. So we said that was not a very good strategy, and these were better strategies, and so and so. So we did a lot of tests like this, and secondly, we did 9 tests in a fire training facility representing a small mechanical workshop. We did 13 standard wooden pallets. That's about maybe 3 or 4 megawatts, something like that. And it was a bit more complicated. The firefighter goes in, it sprays from here, okay? and we have positive pressure. We can open this door. We can open up here. This is the second floor, so we can open up a door on the second floor here, and so and so. So we did, again, a lot of different tests. And the third test we did 44 tests in a residential type multi-room firefighting training facility, various suppression techniques, positive pressure ventilation, and so and so. We used 10 wooden pallets, so that's a few megawatts. It's a bit more complicated now. We tried entering through here to get to here. We also tried ventilating out here, and so and so. So we did a lot of different experiments in this facility, and we measured different times. The alarm comes in, the vehicles are moving, they arrive, they start to work, and this is the operational efficiency. So this is the time we were measuring, the end of operation here. So. So basically what I'm going to say is this. Firefighting tactics can't be experimentally investigated. Not many people have actually done work on firefighting tactics. But we can actually get some idea of what's best to do. Of course, it's quite dynamic because it is... things change, the fire changes, it changes with the scenario and the geometry and so and so. But it can be experimentally investigated. And we have done a lot of these. And in a wider perspective, the experiments constitute a basis for further treatment on command and control problems. And based on this type of analysis, we can do all kinds of mathematical or simple models for describing firefighting operations. And of course, there are some basic tactical principles that we sort of came out with. I'm not going to go read through them all here, but I have a book. We could read through these actually, but I'm not going to do it. It's too boring. So read the book. No, but I will leave these books and the paper about this lecture. I will leave it here. You can have a look at it through lunch. My conclusions are basically this. Buildings are getting much more complex, but at the same time, we are getting much more understanding of fire phenomena, computer programs, and so on and so. It's very important not just to take this knowledge to the engineers and the designers, but take it to the firefighters and the fire officers. And we do this by cooperating with the fire service and training establishments. We conduct experiments and provide relevant and appropriate teaching material with a sound scientific basis. So what we wanted to do was to make sure that classical physics, the laws of classical physics and the laws of classical chemistry are not completely broken when we train our people. We want to have it in line with, have it sound. So that was my lecture. And here are the books. So, thanks very much.